a manufacturer of bicycles builds racing, touring, and mountain models. All bicycles are made of both aluminum and steel. The company has available 91,800 units of steel and 42,000 units of aluminum. The racing, touring, and mountain models need 17, 24, and 34 units of steel and 12, 21, and 15 units of aluminum respectively. How many of each type of bicycle should be made in order to maximize the profit if the company makes $8 per racing bike, $12 per touring bike, and $22 per mountain bike? What is the maximum possible profit? So I'm going to approach this pretty much the way we do most of the problems in this class. First thing I'm going to do is I'm going to define my variables. If I don't know what that is, I'm not going to get very far in this problem. And if I look at the problem, I saw that there was a part of the question that said, how many of each type of bicycle? That's my signal right there that I'm going to have to look at those three types, and I'm going to have to assign a variable for those. I could call them x sub 1, x sub 2, x sub 3, but why don't we just call them R, T, and M, because that corresponds then to racing, touring, and mountain. And notice I've included also that it's the number of bikes, not just some other attribute that goes with these bicycles like the profit or something else. So let me write those over to the side here. And now let's go on to the next part of this problem, which is, what are we maximizing? Well, if you look up at the problem statement, it said we're going to maximize profit, and then it tells me where that profit comes from. So based on that, I'm going to write out P equals 8R plus 12T plus 22M, because I know one racing bike gives me $8 of profit, so our racing bike is going to give me 8 times R. One touring bike gave me $12 of profit, so T of them will give me 12T in profit. One mountain bike gave me $22 in profit, so M of them will give me 22M. And I'm also using the letter P for profit instead of Z. The letters really don't make a difference here. You just need to keep working with them all the way through the problem. So let me go ahead and write off what my objective function is to the side here. And now, do you see any wording that indicates an inequality? So if I look up in the problem statement, it says the company has available 91,800 units of steel and 42,000 units of aluminum. That's basically telling me I can use any amounts of steel and aluminum up to that level. So I know I'm going to have an inequality that's less than or equal to 91,800. This is my steel inequality. Well, I know one racing bike takes 17 units of steel, so R of them will take 17R. I know one touring bike takes 27 units of steel, so T of them will take 27T, and one mountain bike takes 34 units of steel, so M of them will take 34M. So I add all those up, and I know that the amount of steel that I use has to be less than or equal to 91,800. Now let's do the same thing for aluminum. For aluminum, I get 12R plus 21T plus 15M. Those are the individual amounts of aluminum, and I can't use more than 42,000 units, so I get less than or equal to 42,000. Do the non-negativity constraints apply? They certainly should, because the numbers of bikes that I'm going to be using should come out to be greater than or equal to 0. We should have non-negative numbers there. Here's my linear programming problem. Maximize P equals 8R plus 12T plus 22M. Subject to the constraints, 17R plus 27T plus 34M is less than or equal to 91,800. And also to the constraint, 12R plus 21T plus 15M is less than or equal to 42,000. And then I know each of my variables are non-negative. You'll notice that this fits into the standard maximization problem because my constraints are less than or equal to a non-negative number. We have the non-negativity constraints, and we're trying to maximize the objective function. So let's go ahead and start getting our initial tableau. The first thing I do is I take all of my variables and I put it on the left-hand side of the objective function. So I get minus 8r minus 12t minus 22m plus p equals 0. Now I'm going to take my second constraint. I'm going to add some amount to the left-hand side called S1. And when I do that, I get 17r plus 27t plus 34m plus S sub 1. It's just big enough so that it's equal to 91,800. Do the same thing to the second constraint. I get 12r plus 21t plus 15m plus S sub 2. Now that's going to be equal to 42,000. So there are the three equations that are going to give me the initial simplex tableau. Now, just like I mentioned before, because we have to add something to the left-hand side to make it equal, the two slack variables that we've just come up with have to be greater than or equal to 0. So I've gone ahead and put the names of the variables above the columns in this 3x7 matrix, and I can look down here and I can see the coefficients that correspond to my equations up above here. So for instance, the second row, 12, 21, 15, 0, 1, 0, 42,000, corresponds to 12r plus 21t plus 15m plus S sub 2 equals 42,000. Now that I have this particular initial simplex tableau, I could go ahead and find the basic feasible solution that corresponds to this. Remembering the non-basic variables here would be r, t, and m. They'd all be set equal to 0, and I think it's pretty obvious that if I do 0 racing bikes, 0 touring bikes, and 0 mountain bikes, I'm going to make profit of 0, and if I'm trying to maximize profit, that's probably not the optimal solution. In the next section, we'll go ahead and find out how we should pick the pivot here so that we find a basic feasible solution that's optimal.